Good evening, my dear warriors. Welcome to the dual nature, photoelectric effect and photons Conquer session, your NEET Conquer series, which is meant to teach you in detail right from basics with problem practice so that you get that confidence when you're solving problems and attempting all the mock tests. So this is your captain, your physics educator, Captain Shreyas, live. I hope I'm audible as well as visible. Do let me know in the chat box. Yes, there was some timing issue. I think my lecture timing clashed with Wazim sir's class. So I had to shift it to 7:15, wait till the class is over. Yes, looks like I'm live, audible, and students are here. Nice to see all of you. Nandini, Nigamat, Srivasan, good evening. Kishore, good evening. Dr. Ritigna. Hello, Vania. Hello. Good evening. Nice to see all of you out here. Nice to see. Good evening, Umar. Good evening. So, before we forget, remember that you have to smash the like button to proceed, because that shows your interest not just towards the channel but also towards the NEET exam. And YouTube understands that really well, and when you subscribe and like this particular channel, YouTube will show you related content, and you will never miss an opportunity. You will never miss the chance to see a lecture. So you will be up to date with the latest regarding to NEET. So thank you for liking and thank you for subscribing. And if you are not yet a part of the Telegram channel, make sure you are a part of it by joining with the link in the description box below. And yes, let me also tell you that Avenger 3.0 is up and running. It's going to start next week. So like many of you might be knowing that we are teaching for the NEET 2024, be it 11th, 12th or dropper students. And almost 70% to 75% of the syllabus is going to be done. Now the remaining 25% is also very interesting, and I want you to attend those classes live. So there is a link which is there in the description box saying Avenger 3.0. Make sure you check that link and join the Avenger 3.0 batch. 25% will be live, and whatever sessions were done previously, don't have to worry. You will get all the recordings as it is. Okay, there are mock tests, there are assignments, everything. We have a nice group with lots of discussions which happen with all the students and the teachers. So make sure you are a part of it. Okay, make sure you use the coupon code CAPTAIN to join not just that batch, but even if you are joining the subscription, be it Unacademy subscription, be it Plus or be it Iconic. So those are the subscriptions, and through those subscriptions you can avail any number of courses, as many number of courses as you want. But if you feel, no sir, I just want your course, then that option is also available. Check the link, and you just have to pay, I think, around close to 4,900 or so odd rupees for joining that Avenger 3.0. Okay, so the coupon code is CAPTAIN, CAPTAIN. That's my coupon code. Make sure you are a part of it. Right, so let's begin. Good evening. Is the last section for physics? Yes, in your 12th standard book, this is the last section of the physics. Good evening, Sidhu. Hello, Achus. Nice names, yeah, you guys got. Sidhu, you always greet someone by saying good evening, not good night. Good night is when you are saying bye-bye. Okay, chalo. Now, there are some very interesting properties of photons. See, what is this chapter all about? Photons, photoelectric effect and dual nature. So, when I say, light travels from point A to point B, I turn on the torch, the light goes, or there is a bulb. Imagine this is a bulb. Okay, the light is going here, the light is going here, the light is going here. Light has two kinds of characteristics or two personalities. One personality is called as wave. The second personality is called as particle. The second personality is basically called as particle. Keep this in mind. These are the two different personas. These are the two different personalities or behavior of basically light. Light can behave either as a wave or as a particle depending on the situation. You might be wondering, sir, what are those personalities, traits? So if light is behaving like a wave, then it can undergo refraction, it can undergo reflection, it can undergo interference, okay, interference, it can undergo diffraction, it can undergo diffraction, it can undergo polarization, okay, polarization. All these are wave characteristics. You might have had friends in front of teacher, full serious, full studious, in home or maybe outside, full on dawn, right? Hit students, takes the bicycle, roams around, crashes it, right? Bullies other students, that is outside. And when in the class, in front of the teacher, full serious, front bencher, teacher thinks that student is the best student. So that is the same kind of behavior light also, gives. So sometimes like a wave. So all these are the traits of waves. But when you talk about particle, my dear warriors, when you talk about particles, right? When you talk about that particle behavior, then it will have momentum. It will have a momentum, right? It will have some velocity, right? It will have some kind of, I would say, kinetic energy. It will have some kind of kinetic energy, right? All these are, traits of particles. All these are the traits of particle behavior. They can collide, right? They can, transfer the momentum when they hit each other. All those things are the traits of particle behavior. So, to summarize, light has dual personality disorder. One is particle, one is wave. And the wave nature of light is a separate chapter. We have spoken about it or will speak about it in something called as the electromagnetic waves. Light is an electromagnetic wave. But when we say light is a particle, that particle behavior is called as photon. What is that particle behavior called as? Photon. Is that clear? Yep. Is that understood, my dear warriors? Everybody give me a thumbs up till here if it is clear. The wave nature is described in a separate chapter. Electromagnetic waves, light waves, separate chapter. But the particle nature, that is photons, that's what the particle of light is called. Okay, which shows behavior like momentum, collisions, velocity and all those things. So let's discuss more about the particle of light. Let's discuss more about the particle of light. The particle of light, which is basically a photon. Everybody? Awesome. Thank you for giving the thumbs up. HP, Jyoti, Nandini, Ravinath, Hania, Mansha. Very good. Now, the first important property of this particle, which you call as the photon. This photon, do not think that, sir, I can locate that photon. Sir, I saw under microscope. You cannot see it under microscope. You can feel it, but you cannot see it. It's not like round. Sir, in the book, no, in one diagram somewhere on Google search I saw, sir, photon is like this, sir, sphere, like cricket ball. All those things are nonsense. Photon does not look like a cricket ball, point, particle, dust particle. These are all your imagination or just to show, represent, just to make students visualize. Nobody can see that photon as per se. Nobody can see, oh, this is a surface, oh, it is oval, oh, it is quadrilateral. No, nobody knows how it looks like, but it's just a particle. Main things are the energy of a photon. The energy of a photon, is given by EP is equal to hf, which is also hc by lambda, where h is basically your Planck's constant, whose value is 6.626 into 10 to the power minus 34, all right, in SI units. C is obviously the velocity of light, which has an approximate value of 3 into 10 to the power 8 SI units again. F is frequency, lambda is the wavelength. We all know We all know in waves chapter we have studied this. Speed of light is frequency into wavelength. This is a standard formula. So F will be c divided by lambda, which is what I have substituted right over there. This becomes an important formula. This becomes an important formula. This is also called as the quanta of light. Quanta of light. Quanta of light, which is also an energy packet, which is nothing but an energy packet. Energy packet. Light energy does not go continuously, it goes in packets. It goes in packets. Imagine a person packing some glucose powder, okay, in one sachet or a packet, and you're like, okay, take this. Okay, put that glucose powder, energy, okay, pack it, send it. So light's energy also goes in packets, guys. Okay, it will always go in packet. And the packet size or the packet energy is this one. The packet energy is basically this hc by lambda or hf. More frequency, more energy in that packet. Less frequency, less energy in the packet. Now guys, you only think and tell me, out of blue color and red color, who has more frequency? Red color versus blue color, who has more frequency? If you know the wavelength, you know it is inversely related. Red has long wavelength. Violet blues have short wavelength. Short wavelength means high frequency, right? So think about it, my dear warriors. If I take blue color, which has very high frequency, versus red color, which has very low frequency, exactly, think about it. Won't the blue energy packets be higher or bigger in value? So the blue energy packets, each one of them is HF, 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 like that. They will be bigger energy versus the red energy packets, which will be slightly smaller. I mean, the energy sizes will be slightly smaller. This will be HF, this will be HF, this will be HF, and so on and so forth. Right? These energy packets are smaller. So I can definitely put a bigger than, more than symbol over here. These energy packets are bigger because frequency is higher, because the wavelength is shorter. Here wavelength is more, so frequency is less. So hence, and energy packets are, smaller in sizes. That's what I would say. Everybody fine till this point? Did you understand the difference between the blue and the reds, or any higher wavelength and lower wavelength, or higher frequency and lower frequency? So this is the comparison of the energy packets. This also tells you light does not travel in continuous energy, but in energy packets. Each packet is called quanta of energy, which is also in the energy packet of that light. Good evening, Tej. Awesome. Looks like everybody has understood till this point. So let's proceed further, guys. Let's proceed further. Awesome. The next important characteristic of a photon. The next important characteristic of a photon is that the photon has a momentum. The photon has momentum, but mass is not defined. Mass is not defined. Okay, remember this very, very important thing. The photon has momentum, but the mass is not defined. I'll explain everything. Also, photons travel at the speed of light, travel at basically the speed of light, number 2. And one more thing, the rest mass of a photon is assumed as 0, is assumed or taken for granted as basically a big fat 0. So remember one thing, that if I have a photon HF, this is nothing but a photon, it will be traveling at 3 lakh kilometers per second. 3 lakh kilometers per second. That's the speed of the photon. All right. That's nothing but the speed of the photon, no matter which direction it goes. But it will be wrong or illegal for me to say the momentum P is equal to mass into V, but V is C, so M into C. This is completely wrong. This formula can't be used. You cannot say the momentum of a photon is mass into velocity, c being the speed of light. That is illegal. Reason being, m is not defined. Reason being, mass for a photon is not defined because of relativity effects. You don't have to go and struggle over those topics, but just remember, when you are moving at very high speeds, then Albert Einstein's relativity effects come into play, because of which you cannot use your traditional formulas which you have been learning. Mass into velocity works for small speeds, but for higher speeds it doesn't work. Is that clear? Is that clear? This formula won't work. What is the formula which will work? The formula which will work is this one. P is h by lambda. H by lambda. We can do one small modification here. We know h by lambda means it is hc by lambda divided by c. Cc anyways cancels, I get this. The reason why I did it is because hc by lambda is energy of the photon. So it is nothing but energy of the photon, and divided by c. So P is E by C or h by lambda. Both are okay. Both formulas are fine. So this is the formula which is used for calculating the momentum of a photon. It is used for calculating the momentum of a photon. Is that clear? You cannot use mass into velocity, my dear warriors. Is that right? Yes, Heisenberg's uncertainty principle is applicable everywhere. It is not a special rule only for electrons or only for protons. It is applicable everywhere. Yes, physics and chemistry, Arogya, obviously available in the Avenger 3.0. Definitely. Awesome. Cool. Let's move ahead, guys. Let's move ahead. Yes. 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 All right. Sai, what do you want to know? Please reply. Yes, it will be conducted. Just give me some time. For now, you can watch the lectures here. There is some plan which I am making and I am pushing for the JEE students as well. For now, please continue over here for, in the NEET channel. There will be something awesome which will be coming up very soon. I know many students are dependent for JEE 2 on me, right? I will look into it. Next important thing which you should know about. Okay, we have discussed about mass, momentum, and also how fast the photons travel. We have also discussed about the energy of the photon. Now the next important characteristic is photons follow law of conservation of energy and momentum, both law of conservation of energy and momentum. Like when a photon collides with an electron, the electron will get some energy will get transferred. Also, because the photon was moving, it will have some momentum. So because of which the electron will start moving, with a new velocity. So it is like colliding. So momentum gets transferred from one body to other body. All those laws are still applicable. There is no doubt about it. These are universal laws. These are universal laws. It's not like only in the bigger world it is applicable, in the quantum world or in the big macroscopic scale of the universe it is not valid. There is nothing like that. It is valid for the minute or the minutest things till the largest of the largest things. So it is still applicable. But the interesting part is the number of photons may not be conserved. Reason being, since it can be absorbed or even released. This is one very interesting thing. Look at this. Imagine that there is a photon. And this photon of light is traveling and it happens to hit some electron or proton or nucleus or some atom or whatever. Example, this atom. Now, this is before the collision. This is basically before the collision. After the collision, maybe the atom absorbs it and maybe it is now in an excited state. So it's an excited, very, very happy atom. We'll be talking about this in atomic structure as well, and some of you might have already studied it in chemistry. So this photon is getting absorbed. It's nowhere to be seen. Is the number of photons conserved? Obviously not. Obviously not. There was one photon here, there is no photon here. It's not like the photon is sticking inside the atom. No, that is wrong. Okay, the photon is not sticking somewhere inside the atom, it is gone. It's absorbed completely. Yes. Because we'll be doing it there also, don't worry. Yes, we'll be doing it there also on Thursday. So the reverse is also true. An excited atom is very excited. Now it loses all its excitement, comes back to its ground state, natural state. It releases a photon. So from nowhere a photon is created by the difference of the energy. So guys, over here too, you will see photons may not be conserved, but total energy is always conserved. Energy and momentum always conserved. Did you understand? Photons may or may not be conserved, but energy and momentum always conserved. Is that clear? Yes. Sir, if photon escapes, can color change? For a given color, the photon is a fixed thing. If I have a photon, that means it has some color. If the color has changed, means the photon has got absorbed somewhere and a new photon has emerged. It's not like the photon became big, fat, and then the color changed. No, that's not what has happened. It would have got absorbed and a new photon would have come out. So that's why the color can change. All right, in different scenarios. Awesome, awesome. Yes, I will definitely, Buddha Surya, I'm always for you, and you will see me very often now on the NEET English channel. All right, great. The last one, very, very important property. See guys, I have seen so many teachers, so many institutes, they do not discuss all these things. They directly say P is equal to H by lambda and E is Hc by lambda, and they directly go to problems. I don't want to do that injustice to you. I want you to know each and every point regards to photons, because if you are a Shreyas sir student and when you go into the college and this topic comes in some way or the other, you will be the one who would have an in-depth understanding. And that's what, my students always say, even after going to college. Sir, I went to this college, one student of mine went to BITS, and there was some circular motion problem and the student was able to do it very aram se. Other students were struggling, although all students are brilliant, because they were not able to understand some hidden concept. They're like, sir, we just knew the formulas, but we never knew how to actually use it in some crazy tricky situation. But my student was able to do it very nicely. And then he told proudly, sir, you know what, I was studying here under Shreyas sir. So I felt very happy when the student came back and told this. So I want the same thing for you too. Coming back over here, the last one is of light. See, when I say intensity of a light beam, all right, that intensity I is basically the total energy which is coming out per unit time, per unit area. The total energy, this is not energy of one photon, this is the energy which is in total per unit time, per unit area. Now what does that mean? Let's understand. Imagine in a beam of light, a light beam is coming from a torch. There will be so many photons, right? Imagine this is your torch or light source. There will be hundreds, millions, lakhs, crores, trillions, who knows, so many photons which will be coming out. So this total energy, can I say, is the total number of photons into energy of each photon, Time is basically T, area is basically A. Is that making sense to all of you? Everybody with me? Total number of photons into into energy of each photon upon T into A. Let's play around with this a little bit. N by T, I can write it as small n. The difference is N is the total number of photons total number of photons, whereas small n is nothing but the number of photons per unit time. Number of photons per unit time. So capital N by small t is basically small n, the number of photons which are coming out per unit time. You might have seen these kind of terms even in solenoid. Capital N is the total number of turns and small n is the turns per unit length. Per length, how much is the turn? So same kind of symbols we are using over here, and this is energy of the photon, the whole thing divided by A is nothing but the intensity. If you are wondering what the unit could be of intensity, well, I'll just put it right over here maybe. The unit of intensity will be joules per second per meter square, but joules per second is watts, so it is watt per meter square. That's how intense the light beam is. Lot of energy is coming in 1 second and per unit area, so it is very intense. If it is spread out on a wide area is large, so then the intensity will go down because that same energy is distributed. Intense means all light energy is concentrated. Like when you use a magnifying glass, all the rays converge at a point, so the intensity increases. So that is the meaning of intensity, guys. Now please remember, EP is the energy of a photon. So if you want, you can also write this as like this. So intensity is NhF by A. So this becomes your formula for intensity of light. N is the number of photons coming out per unit time. And sometimes you might do one small change. You might take intensity and area and multiply it, IA, and you will get it as NHF. What is intensity into area? Basically, if you remove area, you'll just get energy per unit time. If I take area on this side, I'll just get energy per unit time. What is energy coming out per unit time? It is the power. Exactly. So my dear warriors, this will be nothing but the power. So the power will then become NHF. Will just become NHF. Is that right? Everybody with me? Understood? Clearo? Pakka? Very nice. Yes, we'll be studying AC in a separate chapter account. Definitely. Yes, Jeff, I'm always fresh for my students. Definitely. Awesome. 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 Candela is different. No, it is not candela. A lot of people confuse it for candela. No. Candela is a different thing. It is for luminosity. Luminosity you do not study in NEET physics. Okay, that's a more advanced term. Intensity is different from luminosity. Luminous intensity or luminosity, completely different things. So please do not confuse between the two. Okay, cool. Yes, definitely, definitely. All right. So all these are very, very important things. Maybe we can do one or two problems before we go to some objective questions. Here is a very interesting question. Imagine this. Okay, you take a water pipe. Okay, jet spray. Maybe it is there in your toilet. Has anybody used jet spray in the toilet? Yes or no? Avenger 3.0 starting next week. No? Okay. Have you watered the plants using a pipe and you press your thumb? Zoop, that water spray will come. With a lot of force. With a lot of force. Awesome. Very good. So imagine you are using a water pipe and you press your thumb and water is coming with a lot of speed. And imagine your friend is walking by. You put it on him. He will feel hurt, no? Zoop, the water will fall on him with a lot of force. So I have an idea. What if I take a torch? What if I take a torch and I make it fall on somebody's head or somebody's back? Do you think you will feel the same kind of force like you would get from the water pipe or the jet spray? What do you say? Will you get the same kind of force or no? Yeah? What do you think? No, right? Very good. I mean, like, think about it. You take a torch and turn on the torch and you're expecting, oh my God, oh, too much of light. Oh my God, why are you making your light fall on me? Nobody is going to say that. Like, okay, theek hai. They will just get irritated if you put the torch on their eyes. Like, shut up. Remove that torch. Otherwise, if you put it on your back, on your chest, on your leg, on your hand, on your head, behind, nobody will bother, right? Then, does that mean that there is no force or there is very less force? What do you say? Is there no force or there is less force. There is a small difference between the two. Is there no force by light or is there less force by light? What do you guys suggest? What do you guys suggest? Mass of a photon not defined, Jyoti. Rest mass is 0. That is because of relativity effects of Einstein, alright, which we don't have to deal in detail. Just remember that whenever light travels with some speed or any particle, the mass changes and relativity effects come. Very crazy to visualize also, hai na? So let's not get there. Just remember it. Nobody will ask you questions. Find the mass of the photon at this speed. Nobody will ask you. Okay. Yes. Very good, yeah. You guys are very smart, Kiran, Umar, Kailash. We will feel some heat. I agree, Srinivasan. You will feel some heat. Very good, Afra. Very good, Jyoti. Awesome. Yes, you will feel very less force. So less that you can't even feel it, actually. It's worse than an ant walking on your back. If an ant walks on your back, you're like, oh, dear. But if a lizard is walking on your back, you will scream, you will run around, you will throw things. Hai na? So it is not even like an ant walking on your back, my dear warriors. So the question is, if light of intensity I is incident on an absorbing surface A, find the force on it. Find the force on it. So let's try to understand what it means. So here we have the surface. It's basically completely absorbing in nature, and the surface area is A, and we have a lot of photons coming like this, and these photons hit the surface, and that's it. Their journey ends. They get absorbed into the surface, like a black surface. They get absorbed, right? Okay. So how much is the force acting on it? That's what we need to find. Now we all know one thing, that force is the rate of change of momentum. Force is rate of change of momentum, right? So if you want to find the average force, I will just write it as the total change in momentum, upon the time taken. That is the force acting on any particle or a surface or any body. How much is the momentum changing? Now the total momentum, can I say, it is the total number of photons into the momentum change by one photon upon the time interval. Imagine there are n number of trillions of photons. Each photon will change the momentum by some amount. So if I multiply by n, I get the total change of the momentum. Time interval is as it is. Okay. Oh, but wait a minute. I know what is this n by delta t. I will take care of it later on. But I know this n by delta t is small n. N by delta t is nothing but small n. Everybody agree with this? This is nothing but small n. Change in momentum. Finally, they stop. Initially, they had momentum. So can I say it is nothing but p minus 0? Can I say it is p minus 0 because they get stopped? Earlier they were in motion. Now they stop. So the change is magnitude wise p minus 0. Everybody fine till this point? Awesome. Now, what is this p? P is nothing but h by lambda. I hope this is fine. Okay, I have some ideas over here. Why not write this as nhc by lambda and 1 by c. Now what is this? hc by lambda, that is energy of the photon, and n is number of, photons which are coming per unit time. So strictly speaking, this nhf or nhc by lambda is nothing but the power, or I can just say it is I into A, or I can just say it is basically I into A. Well, if you do not believe me, no problem. I will just write this as, NHF divided by A and into A and divide by C. I just multiplied and divided by A, that's all. Because now I know this particular part is nothing but intensity. So this will become just I times A divided by C. So the force is nothing but IA divided by the speed of light. Awesome. We got it. IA divided by C. IA divided by C. More the intensity, more force. More the area, more force. Speed of light is constant. As simple as that. Is that right? Now I can make a small change. What if the surface was not absorbing, but if it was reflecting? If it was reflecting, then what will be the answer? If you are smart, you will give the answer within 2-3 seconds, guys. If it was reflecting, that means the same photons will come back again like this. Then what would be the force? Think about it. In case of absorbing, it was IA by C. If the same surface is reflecting, then what will be the answer? Come on, come on, come on. Tell me the answer in the chat box. I want to see who are the smarties. Who are the amazing warriors? Awesome, Joseph and Rani. Wow, what a name. Very good, Maniraman. Awesome, it should be 2 times. The reason is this. It will no longer be P minus 0. It will be P minus P. So basically it will be 2 times of IA by C, since momentum changes twice. Momentum will change basically twice. Yes, that is very, very important. That is very, very important. Is that clear? Absolutely. Everyone? Awesome. Now, in some problems, I will give you a trick to simplify the calculation. I'll give you a trick to basically say simplify the calculation. Say for example, the wavelength is given to you and you have to find out what is the energy of the photon. Example, imagine wavelength is given to be 400 nanometers. Find the energy of the photon. That is the question. What you should do is observe. There is a simple calculation trick, and the trick goes like this. Energy of the photon is hc by lambda, right? So h is basically 6.62, 6 into 10 to the power minus 34. Speed of light is 3 into 10 to the power 8. Wavelength in meters, okay, in nanometers, if I put it, wavelength in nanometers, then I'll have to multiply it with 10 to the power minus 9 to convert it into meters. Whatever answer I get over here will be in joules, right? The answer that I get will be in joules, right? Everybody with me? But most of the times, you do not want to write the answer in joules. Joules is a very big unit for quantum world. Joules is a very big unit for the quantum world where the energies are in negative powers of 10. So for such minute energies, there is a different unit, and that is called as the electron volt. So what you do is just take this 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8. All right, the whole thing. Lambda is in nanometers into 10 to the power minus 9 and divided by 1.6, 10 to the power minus 19. You multiply by E, divide by E. If you notice, I have divided by the electron charge, which is 1.6 10 to the power minus 19. Also multiplied by it, no problem. Okay. So this will be now electron volt. This will be now electron volt. Actually speaking, this is E coulombs. This is basically E coulombs into V, or I can say volts over here. All right, this is coulomb into volts. Now this number approximately comes out to be 1240 divided by wavelength, but in nanometers only. But this is electron volt. This is electron volt. This is the energy of the photon in electron volt. You can also say it is 12400, but wavelength in Armstrong. That is electron volt. So if it is nanometers, it is 1240. If it is Armstrong, it is 12400. That's all. That's the change. Is that right, everyone? Great, great. Yes, yes, yes. Awesome, awesome, awesome. Is that clear? Is that clear, everyone? Great. Shall we proceed? So what will be this answer, guys? Come on, let's see if you guys can tell me the answer within maybe 10 seconds. maybe 10 seconds. Come on, come on, come on, come on. Come on, come on, come on, come on. What will be the answer for this? Use, this is in nanometer, so use 1240 divided by 400, 1010 cancelled, right? So 124 divided by 40. Come on, how much will it be? 31, but divided by 10, 31 divided by 10. So it will be 3.1 electron volt. 3.1 electron volt. Awesome. So this is how you solve the problems on energy of the photon. If they ask you, what is the momentum? What is the momentum of the photon? What is the momentum of the photon? What will you do? One option was h by lambda. I would suggest don't use this because it will be a very complex calculation. Or we also had E by C formula, energy of the photon by C. I think this is better formula, right? And that's how you can solve it. So energy of the photon is 3.1, but it is electron volt, do not forget. Speed of light is 3 into 10 to the power 8. Do not forget to substitute the value of E, or else you will get a wrong answer. Roughly speaking, 3.1 and 3 will roughly cancel, no? 3.1 and 3, roughly they are like 1 point something. So that's okay, you can take it as 1. So all that is left is now the value of E, right? This volts will all go off, this will have that meters per second and all of that. So eventually you will get basically E kg meter per second. E kg meter per second. E is nothing but roughly 1.6, 10 to the power minus 19. So that is the momentum of that particular photon. That is the momentum, but this is not exact. This is an approximate value. Please mind that. Okay, because these two values, when they cut, they cancel. You will see approximately they will be 1. Approximately they will be 1. Yes, very nice. Oh, 10 to the power minus 19, guys. Not, oh, and I think I forgot the 10 to the power 8 below. I'm so sorry. This was 10 to the power 8 over here. So once this 10 to the power 8 cancels with this, once this 10 to the power 8 cancels with this, it will become 1.6 into 10 to the power 8 goes on the top, it will become minus 27. Minus 27. 1.6 10 to the power minus 27. Yes, yes. It is not 10 to the power minus 8, bacha. This is 10 to the power plus 8. This is 10 to the power plus 8. Be careful. You have to bring it on the top. That negative power with this negative power will add and it will become minus 27, guys. Be little careful. Yeah. So it is a very, very small number. It is a very, very teeny mini momentum. So don't expect too much of force. Alright, do not expect too much of force. So let's start solving some questions. But before that, one more small thing that I would like to tell you, that we will be now slowly transitioning to something called as the photoelectric effect just after this. And these photons which we just described, we just discussed all the properties, right? So these photons can actually knock out some electrons, which is called as the photoelectric effect, which we'll be discussing now in a bit, right? So keep these things in mind. All these properties will be useful in that particular set of problems and in particular theory, okay? So keep those things in mind. So I think this question is from photoelectric effect. We'll do this in a bit. This has come wrongly over here. Let's start with this. The relationship between the photon and its wavelength. The relationship between the photon and its wavelength. Energy is directly proportional to wavelength. Energy is inversely proportional to the wavelength. Energy is independent of wavelength. None of the above. What do you think? Come on. Very good, guys. Energy is inversely proportional to the wavelength. Energy is inversely proportional to the wavelength because energy is basically hf, which is basically hc by lambda. hc by lambda. Awesome. Yes. So you can see energy is inversely proportional to the wavelength. Awesome. Next question, the photon of frequency nu, you can use f or nu, okay. Momentum associated with it, if c is the speed of light, is how much? What is the momentum associated with it? Come on, think about it. Nu by c, nu v by c square, h nu c, h nu by c. What is the momentum associated with it? Remember, momentum is h by lambda, right? So what can you say? What can you say? H by lambda. So is there some option like this? Is there some option like this which can be somehow, you know, converted into frequency? Think about it, guys. Think about it, guys. Speed of light is nu into lambda. So if you take lambda below, what will happen? 1 by lambda will become nu by c. It will become nu by c. So just put h into nu divided by c. H into nu divided by c. Where is such an option, guys? Very good. Option D. Very good, Vedanchani, Senthil Kumar, Josephine, Rani, Ravina. Awesome. Yes, you can join the recorded lectures and you can get access to it completely. Don't worry about it. Even if you join now, I think you are making the best decision of your life. Moving on to the next question coming up on your screen. A 200 watt sodium lamp emits some light of this much micrometer, assuming it to be 25% efficient in converting the energy into light. The number of photons that the light emits is how much? Just some time back I gave you the formula for power, and the formula for power was n times of hf. And this is exactly what is asked. What is this number of photons of that light which is emitted per unit time? So it is basically P by hf. But there is a small catch in this. This P is not 200 watts because it is only 25% efficient. So strictly speaking, that power is 25% of how much? 200 watts. Of 200 watts. So it is basically 1/4 of 200. That means it is basically 50 watts. Now you just have to substitute everything. So the power is basically 50 watts. H is not given, but I think its wavelength is given 0.6. So 6.6 into 10 to the power minus 34. Instead of F, I can put it as C by lambda. Speed of light 3 into 10 to the power 8. And I divided by lambda, which is 0.6 micrometer, or 6 into 10 to the power minus 7 meters. 6 into 10 to the power minus 7 meters. This is, remember, 0.6 into 10 to the power minus 6 meters, which is the same as 6 into 10 to the power minus 7 meters. So I've put that over here. You can see many things might get cancelled and you will get the final answer in some value into 10 to the power something. Most likely the answer comes out as 10 to the power 20 with 1.5 multiplied outside of it, roughly. So just check this out. If you roughly get it as 1.5 into 10 to the power 20. These many photons are coming per second from that light bulb. Isn't it crazy? Yes. Awesome, right? Mohammed, whatever price is shown on the website, use that, but make sure that you use the coupon captain so that you get the discount. So that same price, I don't remember what the price is, but it will be that same price. Okay, so you'll get all the content as it is. You are not missing anything, just that you are missed some classes. So obviously you'll get those recordings as it is with assignments, whatever is there. Don't worry, PDFs, everything will be there. Okay. Now let's go to photoelectric effect. Let's talk about photoelectric effect in a very simple manner. I'll explain you. I'll show you the graphs. I will explain you the experiment, everything. Don't worry about it. I was telling you that remember the properties of photons, because those properties of photons will now be useful for photoelectric effect and their formulas and other things. Now understand, when you take a metallic surface or any surface, you can knock out the electrons out of it. Imagine there is a metal surface. I can knock out the electrons. I can knock out these electrons from it. I can knock out these electrons from it in three different ways. All right. The first one is called photoelectric effect. Photoelectric effect. The second one is called thermionic effect. Thermionic effect. The third one is basically called as the field effect also. Field effect or breakdown. Field effect or breakdown. So the first one is photoelectric, second one is thermionic, third one is field or breakdown effect. What are these three things? Just like the name suggests, photo. Photo means because of photon. A photon causes the electron to be knocked out. So imagine light falls on this surface. Photons are falling on the surface. They collide with the atoms and the electrons and they throw those electrons out. That is called photoelectric effect because it is happening because of photon. Understood everyone? Understood everyone? So light falls, that means photon falls. What does photon have? Momentum. It has force. It knocks that electron out, photoelectric effect. Second one, thermionic, thermal. So basically you heat it. You basically heat it. What will happen? The atoms become excited. They start shaking. They start colliding. Once they collide, what will happen? These electrons will hit each other. They get, affected. Dish, dush. Full fighting will happen. And these electrons, bichara people, collateral damage, these get ejected out because of heating that, surface or because of heating that body. That is thermionic emission. Third one, field effect breakdown. Just like the name suggests, it is because of strong electricity or potential difference. Best example, lightning. Imagine from the clouds and the earth, right, because of rubbing and so many other things, there is an electric field which is being created between the clouds where the rain falls from and the ground. Imagine it like a capacitor of very strong voltage difference, very strong electric field, high voltage to low voltage, potential difference, electric field, and it becomes so large that the electrons get plucked out from the atoms. The field is so strong, it plucks out those electrons from the atoms, and that electric discharge happens from the clouds via the least resistance path in air to enter into the ground. That is lightning. Lightning means it is electricity, but not in a conductor, in a non-conductor. Crazy, right? Air is not a conductor of electricity, but it became conducting because the breakdown happened. It gave up. It broke down completely because of the strong fields, and that strong field sucks those electrons out of the atoms, and these electrons flow in that particular region. So that is field effect. Did you understand these three things? Crazy, right? These are the three different phenomena by which you will see electrons can be ejected out from any surface. Thermionic, photoelectric, and obviously you have the field one. Cool. I hope you guys have smashed the like button. In case you have forgotten to do so, please do that right now. It's a long time since you have been watching this class. You need to at least do that. And yeah, if you're not yet subscribed, hit the subscribe button right away right now. We are going to concentrate only on this. These two things are only there in theory part, saying that these are the only ways of creating the electron. Apart from that, nobody is going to ask you questions on this. Just you should know the three categories. So what is this photoelectric effect in detail? Let's study. Imagine you have a metallic surface. Imagine you have a metallic surface. Obviously, there are many what? Free electrons in it. There are many free electrons in it. Just because somebody says free food does not mean it is literally free. You have to make the effort to go there. You have to make the effort to stand in the line. You know, when you go to a temple, you get free food. But you have to stand in the line, right, to get that prasadam. Awesome. Same way, when they say free electron, it's not like, oh, freely available, let's take out the electrons. No, no, no. You need to do some effort. So, these free electrons are there, and let's say light. Let's say light. So, this is basically light. That means that is photons are incident on it. Then these free electrons may get knocked out under certain conditions, but they will get knocked out only if the light has a bare minimum amount of energy. Like I said, nothing is free in life. Even if they say free electrons, it is not freely available. You need to put in some effort, right? You need to put in some effort, right? So maybe that effort is 2-3 electron volts. So I need to give it 2 or 3 some kind of electron volts to pluck that electron out. Then it is like, yeah, I'm free. Just like your friend at your home, at their home, sorry. He says I'm free, but he will be like, come pick me up. Happens or no? Has it happened? The friend said, yes, I'm free, but you have to pick me up. You bring your bike, you bring your car, or you just come walking to my house, I will come walking with you. Same way, you have to put in some effort. Then that electron gets knocked out. That means your friend gets knocked out with you, and you both can go roam around wherever you want to. So there is a bare minimum. If you say, no, I'm not going to give that energy, I'm not going to make that effort, this electron, free electron will say, get lost boss, I'm going to chill in this metallic surface. I am not going to come out. It will be chilling over there in that metallic surface. It's not needed for it to come out. Yep. Is that right? Very good. Yes. So now this gets knocked out. Obviously, it has some kind of kinetic energy, and at the same time, I would say there is a bare minimum energy to knock it out. That bare minimum energy to knock it out is called as the work function. The symbol for that is basically phi. So looking at all these things, I can clearly make an energy equation, because remember, photons do follow laws of conservation of energy and momentum. So I can say that the energy of the photon is equal to that bare minimum energy I need to give it. This guy had 100 electron volt. This guy said, give me at least 3 electron volt to take me out. Okay, I gave you 3 electron volt out of that 100 to pull you out. What will that remaining 97 be doing? It will be in kinetic energy. So phi plus basically the kinetic energy of the electron plus the kinetic energy of that electron. This famous equation is called as the Einstein's photoelectric equation, and just for this equation Einstein got Nobel Prize. Just for this equation Einstein won Nobel Prize. I know you guys are thinking, sir, you know how many times I have written energy equation in work power energy chapter? I have not even got one praise, sir. Instead I have got scoldings for, doing it like this, doing it like that. Nobody appreciates me, sir. I understand your feelings completely. Even I am feeling sad. Even I have written so many times, taught energy equation so many times. Nobody gave me Nobel Prize. Einstein wrote this simple equation. What is this? Energy of the photon is some energy required to pull it out, plus the remaining energy is kinetic. For that he got. Crazy, no? So that's what it is. Okay, let's play around with this equation a lot, because this equation, although it looks simple, there is a lot of things with regards to that. So let's have a look at it. Now imagine I take a metallic surface. And I take 3 different scenarios. First time I have blue light which is falling onto it. Next time, let's say I have yellow light just falling onto it. And let's say in the third case, I have red light which is falling onto it. Obviously, red has a very large wavelength. Now, where do you think it's more likely that the photoelectric effect will occur? Where do you think it's more likely that the photoelectric effect will occur? Yes, Kishore, modern physics is the last section of physics, yes. Obviously, more likely to be occurring in this part, right? Why? Because the energy of the photon is very large. So, here, the energy of the photon is basically very less. Whereas, if you say over here, the energy of the photon is very, very large. So, there is very good chance that photoelectric effect might occur, and you might probably see some electrons getting knocked out over here. Some electrons getting knocked out over here. Here the energy is less. Maybe the electrons get knocked out, but not so many in number, few of them. In this case, the energy of the photon is so less that it is in fact lesser than the work function. So no photoelectric effect occurs. No photoelectrons over here. No photoelectrons over here. The reason being the energy of the photon is less than the work function. In this case, I can say maybe the energy of the photon is more than the work function. Maybe for a certain wavelength, the energy of the photon just happens to be equal to the work function. So that means this is the most critical case. This is basically a critical case where the energy of the photon just happens to be equal to the work function. It just plucks it out and like, okay, you are free now. Pavam, that electron will not have any energy. Here, out of 100, 3 went in plucking it out. The remaining 97 was as kinetic energy. Here, the photon's energy is only 3. It took all that 3 electron volt to pluck it out. Now it's like, okay, you are free. That electron will like, what nonsense. You just gave me 0 kinetic energy. But yeah, I am at least free from the surface. It's just been plucked out. Photoelectric effect has just occurred. So this is a critical case, and this is also sometimes called as the threshold case. So this will be Hf0 is equal to phi, or you can also say Hc by lambda naught is equal to phi. So what is this F0 and lambda naught? So F0 is called as the threshold frequency, whereas lambda naught is called as the threshold wavelength. Obviously, in this case, I can say the frequency of that red light is definitely less than the threshold frequency over here. In this case, I can definitely say the frequency is more than the threshold frequency of that particular surface. Correct? It is more than, here it is less than. So no photoelectric effect. Here there is photoelectric effect happening. This is a critical case where the electrons are just emitted, just coming out, right? So that is what it is. Wavelength wise, if you talk about it, wavelength wise it is exactly opposite. This is not the minimum, this is in fact the maximum wavelength. So actually here the wavelength is more than the critical wavelength. Keep this in mind. More than the critical wavelength, and in this case the wavelength is less than the critical wavelength. Less wavelength means more frequency. More wavelength means less frequency. Keep that in mind. So that's why it is inversely related to it. Is this chart, is this mind map, is this slide very, very clear? Yes, please let me know. Everybody with me? Everybody with me on this? Let me know. How many of you are clear till this point? Is this slide very, very clear? When photoelectric effect occurs, when it doesn't occur. And these things are very important. Hf0 is phi and Hc by lambda naught is also phi, one and the same thing. Then another important thing is that, let's say there is a metallic surface. There is a metallic surface. Maybe, you know, light was falling onto it. Maybe light was falling onto it. So these are basically your photons. These are basically your photons, which is nothing but light. This is your metallic surface. And let's say electrons were ejected out. These are electrons which were ejected out with a good amount of speed. But here is what you did. Here is what you did. On this side, you took another plate. So imagine here you took another plate. Let me see if I can create a duplicate out of it. Yes, I can. And what I did was I connected this plate to the positive terminal and I connected this plate to the negative terminal. What do you think will happen, guys? What do you think will happen? These electrons which are ejected out, this is positive plate. Positive attracts negative. Positive attracts negative. Negative repels negative. Negative will be like, get lost negative. So it is pushed out, it is pulled in here. So obviously they will accelerate. They will accelerate. They will be so happy. They will be accelerated. They will be accelerated. Agree? So even those weak electrons with very low lallu-pallu energy, they will also come out. Oh, so happy they will be. Yes, somebody is calling me, somebody is pushing me, somebody is also pulling me. Awesome. So they will accelerate. But let's say I connect this to the negative, this to the positive. Oh, that is going to be bad. Positive will say, hey, come back, don't go away. Don't go away. You are negative, please come back. Negative will be like, hey, don't come near me. Get lost. You are also negative, I am also negative. Get lost. I will repel you. Yes or no? Yes or no? Very good. So what will happen? These electrons will lose their speed. They will basically get, I would say, decelerated. They will be decelerated. They will be decelerated. So their speeds will be very, very low by the time they reach here. Imagine, I happen to decelerate it so much that just when the electrons reach here, their speed becomes zero. They come running. They decelerate, becomes slow, drained out. I can't go anymore. This plate, positive plate, like, hey, I told you, no, don't go from me, away from me, come back, you idiot. It will pull you back. All these electrons will make a U-turn. Like, these electrons will fall back onto the positive plate back. That's what is going to happen. So my dear warriors, these electrons will lose out everything that they had and they will again fall back onto this. Electrons will be ejected because of light. They will try to reach here. Just before reaching there, they get pulled back. So you are stopping the electrons from reaching the other side. What are you doing, my dear warriors? What are you doing, my warriors? You are stopping the electrons. You are stopping the electrons from reaching here. So 100% you have applied some voltage. You have applied some potential difference. In fact, this is the reverse potential difference. In this case, it was, I would say, forward potential difference between these two plates. Now it is reverse potential difference between these two things. So that potential needed to just stop the electron is called as the stopping potential. So the reverse potential difference to stop the photoelectric current, is called as the stopping potential. It's called as the stopping potential. In this case, where you have forward potential difference, that means the electrons get accelerated. The photocurrent, because these electrons will go through this and will come over here. So 100% there will be current which will be flowing, a very good current. So I'll call it as a photocurrent. The photocurrent increases. The photocurrent increases due to the forward potential difference. Due to the forward potential difference, that's what happens. So the photocurrent, all the kinetic energy has been absorbed by the potential difference. What does it create? Potential energy, right? The kinetic energy converts into potential, potential converts back into kinetic. Like when you throw a ball up, where does the kinetic energy go? Into potential energy. So where did the kinetic energy of the electron go when it decelerated? In the electrical potential energy. So kinetic energy of the electrons, is it not right for me to say, is equal to energy. Remember, energy was nothing but charge multiplied by potential difference. Charge multiplied by potential difference. So charge is E, potential difference is Vs. Vs being the stopping potential. Vs being the stopping potential. So this becomes the formula. This becomes the formula for the kinetic energy of the electrons. This becomes the formula for the kinetic energy of the electrons. So now coming back to the Einstein's photoelectric equation. Einstein's photoelectric equation. This is what I will say. Observe carefully. Energy of the photon is work function plus the kinetic energy of the electron. I can start substituting each thing one by one. Energy of the photon, hf. Work function, hf naught. Kinetic energy, EVS. So this is valid equation. Or I can also say hc by lambda is hc by lambda naught plus EVS. One and the same thing. These are just different forms of writing the same equation. Different ways of writing the same equation. Is that clear? All these are Einstein's photoelectric equations only at the end of the day. They are all Einstein's photoelectric equation only. Cool? Everyone? Awesome. Guys, concentrate on the class. You guys keep asking, sir, do that, do this. Put it in the comments, no? How do you think I will read some random question while seeing the chats? I will see something related to the topic, right? So something which is not related to the topic, like, sir, do gravitation, sir, do that, sir, what about that? Put it in the comments after the video is over. Yeah, then I can have a nice look at it. Cool? Okay. Hello, JSR. Chalo, let's move ahead. Let's play with this equation now, especially this one, the middle one. HF is HF naught plus EVS. Observe now. See this? HF is equal to HF naught plus EVS. Okay. Let's play around with this, my dear warriors. Let's, bring EVS on one side and let's bring this guy on the other side. So it will become, therefore, EVS will be nothing but I can just say HF minus HF naught. Divide the entire equation with E, it will become Vs is equal to H by E into F minus H by E F naught. This one, so it will become HF by or H by E times of F minus work function by E is nothing but the stopping potential. Why did I write it like this? Observe carefully. Very, very important graph. It has come many times in NEET exam. On the x-axis, I will take frequency. On the x-axis, I will take frequency. On the y-axis, I will take the stopping potential. I'll take the stopping potential. Now observe carefully. Observe carefully, guys. Okay? Just look at this. This Vs, look at it as Y. H by E, look at it as M. F, look at it as X. Minus phi by E, look at it as C. So basically, This m is nothing but my slope. So what is the slope? Slope is h by e. This c is nothing but your y-intercept. What is that y-intercept? It is minus phi by e. It is minus phi by e. So it is an equation of nothing but a straight line. It is nothing but an equation of a straight line. So the graph 100% is a straight line with a positive slope of h by e and a negative y-intercept of minus phi by e. So that means when I show the graph, I think I should show something like this, and this will intersect over here. Stopping potential is never negative. So this is a dotted line because this is physically not possible. So this point will be minus phi by e, and this slope will be h by e. The slope will be h by e. Everybody clear till this point? Everybody clear till this point? Awesome. Now imagine I change the frequency, the stopping potential will change. I change the frequency, stopping potential will change. I use a different metal. I use a different metal itself. What will change? Do you think slope will change or y-intercept will change? Yes, it's the y-intercept which will change. Slope is Planck's constant by the charge of an electron, which is a universal constant. It can't change. So my dear students, what happens is basically if you use a different metal, then slope is still going to be h by e, but the work function will be different. So this is for a different metal, different metallic surface, because remember the work function depends on the surface, depends on the nature of the surface. What is it made of? Is it aluminum? Is it iron? Is it steel or something else? Accordingly, the phi value will change. Surface's nature, that is what it depends on. Keep this in mind. Nothing else. Work function just depends on whether you are using an iron, aluminum, copper, gold, silver, whatever metallic surface. That's all. Right? Crazy, right? This is a very, very interesting graph, very, very interesting analysis. Many questions do come on this particular analysis. Just some time back, I was telling you about how you can accelerate the electron versus decelerate the electron by applying reverse voltage or forward voltage, and how the electrons flow in the circuit versus how the electrons gradually stop going in the circuit. So there is a graph pertaining to that as well. So what is that graph? Well, here it is. Imagine this is 0, this is the current, this is nothing but your voltage which you have applied. This is the voltage. So on this side, I would say it is the forward voltage. On this side, it is basically reverse voltage, so it will be negative. This side positive, this side negative. This I is also sometimes called as the photo current. How much current is flowing? How much current is flowing? I don't apply only any voltage, no problem. Current will go, minimal current will go. So let's say that minimum current is here. I apply more forward voltage, that means more acceleration, more electrons will go on to the other side. Current increases, but it saturates after a point. Okay, why does it saturate? It saturates. The reason for its saturation is whatever electrons were ejected out, all the electrons were called. What more you can get after that? Even if I increase the voltage, if there were hundreds, it's like, imagine this. There is a school. Imagine there is a school. Some kids are coming out of the school after the bell rings in the evening or afternoon. If there is one bus waiting for it, maybe you can collect few students. If there are 2 buses waiting, you can collect more students. Imagine there are 100 buses waiting outside. After a point, if there are only, maybe 200-300 students and one bus can accommodate some 50 to 100 students, that's it. You need 4 or 5 buses. With those 4 or 5 buses, all the students will fill in. What will those extra buses do? Nothing, right? Just by adding more buses, does that mean that you will get more kids out of the school? Arey, there were only some 300-400 kids in the school who came out. Just by putting more buses, you cannot expect more kids to come out, right? Understood? So same way, by applying more voltage, you cannot expect the current to increase. Because whatever electrons will come out from the surface, only that much current will come. After that, there will be saturation. There is no need of that extra voltage. Make sense or no sense? Make sense or no sense? Yep. Yeah, kind of ionization energy, you can relate it to Dhanushri. Yes. So there is no point of increasing the voltage. If you go reverse, this graph goes like this, and it stops. So this is basically minus Vs. This is where the current absolutely becomes zero. What happens? The current absolutely becomes zero. Awesome. Now there is another graph, then I can come back over here, and that is what happens to the current if the intensity of the light changes. Intensity of light changes, what happens to the photocurrent? What happens to the photocurrent? This is very interesting graph, guys. The graph goes like this. If it starts from 0, it will just be a straight line. Basically, current is directly proportional to intensity, because more intense light, what does that mean? It means more photons which are coming. If more photons are coming, that means more electrons are getting knocked out. More electrons are getting knocked out of the surface. If more electrons are getting knocked out of the surface, that means there will be naturally more current which is flowing in the circuit. That's a natural logic which says that more the light intensity, more the photons, more the electrons, more the current. So that's why it is just a simple straight line. Obviously, when there is no current, that means there is no light only, intensity is 0. That's why it should pass from here. If you show it like this, it is wrong, because when there is no light, then there is no current. So bringing that same thing over here, if I draw the same curve, but for a more intensity light, for a higher intensity light, then the graph will go something like this. This is, again it saturates, but for more intense light. That's how the graph shifts. Observe carefully. There will be more current proportional to the intensity, but the funny part is the stopping potential is still the same. The stopping potential is still the same. Guess why? Guess why, guys? Understand this with an example over here. Imagine there are two photons, each of 5 electron volt, which are hitting a metallic surface whose work function is 2 electron volt. What do you think? How many electrons will come out? Two photons, 5 electron volt each, are hitting the metallic surface whose work function is 2 electron volt. How many electrons will come out? Naturally, one photon will collide with one electron, it will knock out one electron. One electron will come like this, one electron will come like this. This is an electron, this is an electron. Each of them will be 3 electron volt. Agree? Everybody? 2 electrons will come out of 3 electron volt each. Now, just imagine this. When I increase the intensity of light, I am not increasing the energy of the photon. Instead, I am asking more photons to fall onto it. I'm just asking more photons of 5 electron volt to fall on it. So naturally, I will have more number of electrons coming out of it, each of 3 electron volt. What are these? These are the kinetic energy. Tell me which has more kinetic energy, this one or this one? Does this electron have more energy or does this electron have more energy? Both of them have same energy. So guys, over here I can say this is more intense light. In spite of that, these electrons, the photoelectrons, still have the same kinetic energy. Naturally, they still have the same stopping potential. You need the same energy to stop them. Same stopping potential. Think about it. They will not require more stopping potential. They still require the same potential, because still each electron has the same energy. Still each photon has the same energy, just that the number of electrons has increased. Yes, I can still say the photoelectrons number has increased. Number has increased, which contributes to more current. Which contributes to more current. That's all. That's all. Isn't that nice, amazing, crazy? Very, very interesting graph. This one also, and this one also. All three graphs are very interesting and unique in their own ways, teaching us new things. Right? Shall we now also see the photoelectric setup, guys? So usually the photoelectric setup happens to be, I'll just show it to you over here. I have a very cool animation for you to see. This is basically a photoelectric setup. Look at this. Do you see this torch? Can you see I can change the color of the light? See this? I can change the color. Blue, violet, green, yellow, orange, red, whatever I want to make it. I can change the color of the light. Okay, great. I can also change the intensity of the light. See, it is becoming more intense. It is becoming less intense, and I can turn it off. It is hitting one metallic plate. It's in a vacuum chamber because I don't want undesirable effects like ionization of gases and all of that. There is another plate which is collecting those electrons, and there is a circuit via a battery connected to the other plate. Notice how I can change the voltage of the battery. I can make it more positive or I can make it negative. Forward, reverse. How many of you are able to see all these things? Don't worry about the values, but I can make it forward battery, zero battery now. This is 0 volts almost, and this is negative volts. So I can help it, I can decelerate it. I can help it, I can decelerate. I can accelerate, I can decelerate. I can do nothing also by making it 0. If I put it at 0, nothing will happen. Is everybody able to see this? Come on, my dear students. Then I'll show you the different things which we can get. Right now, let's not take any help. Let's not take any help. Let's keep it as 0. Let's take it as 0. Okay. Almost 0. It's showing minus 0.2, negligible. It's okay. Now this is infrared light. Let me increase the intensity to some medium value. Let's see if there is any photoelectric effect happening. I don't see any photoelectric effect happening because wavelength is very large. That means frequency is very less. That means energy is very less. It has still not crossed the threshold frequency. So let's basically slowly, there is current versus battery voltage. You can see right over here. And yeah, I think that's enough. Okay. Slowly I'm decreasing the wavelength. That means increasing the energy. Nothing is happening. Red color light, almost orange color light. Okay. Almost yellow color light. Okay. Green color light. Okay. Almost blue color light. Almost violet. Oh, there you see, guys. Do you see electrons coming out? That means somewhere here, that is the threshold. That is the threshold wavelength. You can calculate the threshold frequency also. How many of you realized it? If I keep the wavelength lesser, obviously photoelectric effect will occur. It will occur. You can see more energy is there, more electrons are there. Do you see some electrons are very slow going and coming back also? Notice how some of the electrons go, lose some energy, and again probably even come back also. Okay. Now observe this. I will just increase the forward voltage. They will get accelerated. Look at this. Look at this. They are getting accelerated, and you have reached the saturation current almost. This graph is very interesting. See this. You have reached the saturation current. This is current versus voltage very quickly. If I make the voltage reverse, see now. Observe. If I make the voltage reverse, Okay, it is going to be slowed down, slowed down, slowed down. Probably these electrons won't be able to reach here. Awesome. I've got to, completely stopping the current. These electrons are not able to reach here. I slowly remove the negative voltage. These electrons probably just reach here. Okay, I remove that negative voltage, make it positive. That's it. These electrons get sucked onto the other side. You can see that very easily. Everyone can see that? So that is how this graph is working. Exactly what you would expect. If I increase the intensity, see what happens. The current goes up. More light, more photons, more electrons. That's what is happening. More photoelectric current will flow in the circuit. I can create a reverse voltage and I can stop them also. See this? They got stopped. They are being pulled back. So that is basically your photoelectric effect. I'm pretty sure many of you would not have seen this kind of animated and this way of explanation no matter where you go, right? So I'm very happy that you have understood photoelectric effect. Okay, let's probably solve some questions, but before that there was one question which we skipped at the start. So let's just do that. Okay, what do you think is the answer for this? If a filament is heated, then it emits proton, photon, electron, alpha particle. What do you think? A filament is heated, then that particle which comes out, what does that, what is it? And do you remember what that effect is called? Is it a proton? Is it a photon? Is it an electron? Or is it a alpha particle? Come on, my dear warriors. Yes, it is an electron. And what is that effect called? What is that effect called, my dear warriors? Yes, it is called thermionic emission. Oh, why is it saying photon? Electron. Okay, it is electron. And that effect is basically called as thermionic emission. Thermionic emission. Got it? Very good. Chalo. Let's continue with some more problems. Let's see if you guys can answer this. The voltage of a cell is kept fixed. The wavelength of the light falling on it is changed. How will the current change? How will the current change of that cell? Voltage is fixed. Imagine the wavelength is changed. That means different colors of light are used. One's yellow, one's blue, one red, ultraviolet, infrared. So how do you think will the current change? I feel there is one wavelength after which there will be no current only. Right? Remember, threshold is that wavelength. So if your wavelength is more than the threshold wavelength, then there is no photoelectric effect. If the wavelength is less than or equal to your threshold wavelength, then there is photoelectric effect. So understand that there is only one such graph. I feel there is only one such graph. I think it is this one, where you can clearly see that this is actually lambda naught. Below lambda naught there is current. After lambda naught there is no current. Here, no. A lot of people think this is the correct answer. No. In fact, it is quite the opposite. In fact, after the wavelength crosses threshold, there is photoelectric effect. That is wrong. It's quite opposite. Yes, it is option D. I know some of you had got confused to option B also, like I can see in the comments. Okay, moving on to the next one. Which of the following graphs properly represents the variation of current with intensity of the radiation? Current with intensity, my dear warriors. Which one of them is the correct graph? Which one of them is the correct graph? Come on, think about it. Which one of them is the current graph? Is it the current intensity graph going to be flat, straight line like this, straight line like this, or straight line like this? I just told you that the graph has to be a straight line, number one. Number two, it should pass from the origin. Number three, it will increase when intensity increases. So it is none other than option C. We just did that, right? Current is directly proportional to the intensity. Current is directly proportional to the intensity. Very nice. The work function is this much. For photoelectrons of zero velocity from the metallic surface, the wavelength of the incident radiation should be approximately how much? Zero velocity. That means kinetic energy is zero. We know energy of the photon is work function plus kinetic energy. That means energy of the photon is equal to work function because this guy is zero. So energy of the photon is 12400 divided by wavelength is equal to work function. Work function is 4 electron volt. Remember, this is in electron volt. This is also in electron volt. So naturally, your lambda will be 12400 divided by 4. How much will it be? How much will it be? 3100 Armstrong, right? 3100 Armstrong, right? That's it. That is the answer. Yes, it is a direct question. Correct, my dear students. It's a direct question. Let's go to the next one. Coming up on your screen. There is light of two different frequencies. Energy 1 and 2.5. It eliminates a metal of work function 0.5. Ratio of the maximum speed of the electrons being emitted will be. Acha. So there are two different scenarios here. There are two different scenarios over here. For both these scenarios, you have to think differently. If you see for the first surface, remember energy of the photon is 1 electron volt, is going to go in the work function being 0.5 electron volt, plus the kinetic energy in the first case. In the second scenario, the photon's energy is 2.5 electron volt. Work function is obviously still 0.5 electron volt. Kinetic energy is K2. From this, K1 will be how much? 1 minus 0.5 is 0.5 electron volt. From this, K2 will be, take 0.5 here, it will be nothing but 2 electron volt. Now comes the last part. Guys, the ratio of the speeds is asked. If I do K1 by K2, won't it be 0.5 divided by 2? But K1 by K2, it is nothing but V1 square by V2 square because kinetic energy is half mv square. Kinetic energy is half mv square. So half m got cancelled. V1 square, V2 square is remaining. 0.5 by 2 is basically 1 by 4. So taking square roots on both sides, won't this become 1 by 2? 1 by 2, is it not Captain Shreyas? C for Capto? Just check this out. How many of you got it? How many of you got it? Everybody with me on this? So 0.5 by 2, which is 1 by 4, and I got the answer as 1 by 2. Awesome. Let's go to the next question coming up on your screen. Photons of frequency nu fall on a metallic surface for which threshold frequency is nu naught. Then all ejected electrons have the same kinetic energy. The ejected electrons have a distribution of kinetic energy from 0 to this, or most energetic electrons have kinetic energy h nu. The average kinetic energy of the ejected electrons is h nu naught. What do you guys say? What do you guys say? Think about it and tell me what might be the correct answer. Photons frequency nu fall on the metallic surface for which threshold frequency is nu naught. Then all ejected electrons have same energy, or they have a distribution. The most energetic electrons are h nu. The average energy is h nu naught. I think not all electrons are having the same speed. Some have medium, some have very large, some have very negligible, right? There is a variation. Yes, the smallest will be 0, but the largest, the maximum kinetic energy possible can be given by this equation because it is equal to energy of photon. So the maximum kinetic energy that you can get is energy of the photon minus work function. That means hf minus hf naught. That means h into f minus f naught. This is basically your max kinetic energy. You can't get more than this. Anything else will be less than that. So guys, the most energetic electrons are basically h f minus f naught starting from 0. There will be few with 0 energy, then few with little less, then slightly more, then slightly more, then slightly more, slightly more. Maximum will be, this is the max, this will be h f minus f naught. That's it. You can't go more than that because some energy is always required to pluck out that electron. So the remaining part can be available to you as the kinetic energy. You can't go more than that. Great. Awesome. Chalo. Now, before going to the last part, I think till this point everything is clear. Till this point everything is clear. Very good. Let's go to the last part now, and that is basically matter waves. That is basically matter waves. We just saw that light has dual personality disorder. It can behave like a particle and it can behave like a wave. The wave nature is electric and magnetic field transverse wave, right? And the particle nature, that is basically called as your photons. The particle nature is called photons. The wave nature is electromagnetic field transmitted wave. That is what we have seen. What de Broglie, he's a very famous guy, he thought if light has dual nature, then he thought protons, electrons, neutrons, any mass around you, a cat, a dog, you, your cupboard, the camera, the phone, the mouse, the earth, everything is matter. So even matter means the things which have mass, they might also have dual behavior. Obviously they have particle behavior, no doubt about it, and because they have particle behavior, that's the reason why they have momentum. They have when they hit something, they can transfer that momentum, they can collide with things, they have a definite shape, size, boundary. So they have particle behavior, definitely. In fact, that is that mass, right, which we call. And they also have wave nature. They also have wave nature. That is not electromagnetic in nature. That is called as the matter wave. That is called as the matter wave. That is called as the matter wave. Awesome. Now, what de Broglie did was, he said, if I want to find the particle nature of light, momentum of light, I use P is equal to h by lambda. Remember, lambda is associated with wave, momentum is associated with particle. Left hand side you have particle behavior, right hand side of the equation you have wave behavior. This equation related two kinds of behavior. So what he did was just flipped the equation and he wrote it like this. Right, just wrote it like this. Lambda is h by p. Lambda is h by p. Now this p is associated with particle behavior and this lambda is associated with wave behavior. And for this he won awards. He's like, yeah, this is the wavelength of the matter. This is the wavelength of the mass which is moving. And for that everybody clapped. He got nice, accolades. He became very famous. Crazy, yeah? I mean, just imagine, who would have thought that just this equation, you write this here, just shift the numerator and denominator, and that becomes your new research thesis, and that is exactly what de Broglie did. So this is basically your de Broglie's hypothesis. So sometimes this is also called as the de Broglie wavelength. So a mass which is, no, there is no power, lambda is h by p. So basically, according to de Broglie, if at all there is a mass and I say it is moving with some speed v, so it has some momentum, which is now mv. I can write this formula for mass. It definitely has some kinetic energy, or I can just say the energy, that is kinetic energy, is nothing but half mv square. But at the same time, there is a matter wave associated with it. The mass which is moving, it has some matter, the matter wave is associated. The wavelength is h by p, which is h by mv, I can write this. Some people also prefer writing it like this, because I can write this as p square by 2m. Momentum will be 2mk under the root. So you can also write lambda as h by root of 2mk. You can write it like this. That is also valid equation, guys. So this is sometimes called as the de Broglie's wavelength. De Broglie's wavelength. As simple as that. De Broglie's wavelength. Is that okay, my dear warriors? Everybody with me till this point? Clear? Yes. It's a crazy hypothesis, just flipping the equation and getting a new kind of wave, and there were experiments to prove it, and it was actually proven that light, just like it has two behaviors, even electrons and protons have two kinds of behavior. Now usually what happens, the momentum that is there in our day-to-day life, it's in few kg meters per second. H is in 10 to the power minus 34. So the wavelength is so small that you generally do not see things around you as waves, but you see it in terms of particles, like, you know, an ant crawling or you running or a bus moving. You do not see the wave nature of the bus, the wave nature of a person running, or a wave nature of a cricket ball, because the momentum is huge and the wavelength becomes extremely small and hard to detect. So we neglect the wave nature for day-to-day behavior, but in an atom, the electrons are very teeny-meeny. Electrons have very teeny-meeny mass. Okay, even though they have very high speeds, but they have very teeny-meeny mass. So then this momentum becomes very small. The wavelength becomes very significant for the atomic size. The wavelength becomes very significant, which you cannot ignore for the atomic size. So that's why quantum mechanics comes into play, where you need to account for the wavelength of the electron or the proton or the neutron at that small level. I hope it is clear. I hope it is very clear. Cool. There could be some questions like this, where imagine they tell you charged, let's say charge is Q, M is accelerated by delta V, potential difference, find the de Broglie wavelength, find the de Broglie wavelength, find the de Broglie wavelength. That's the question. So let's understand what is exactly happening. So there was this mass, this charge, it was at rest, it started moving, accelerating, and finally it has acquired some speed. So once it acquires some speed, obviously there will be a matter wave associated with it. There will be a matter wave associated with that particle. So question is, what is the wavelength of that matter wave? So first thing is finding the speed. Without that we cannot proceed ahead. So what I will do, I'll think like this. If I'm accelerating it by some voltage potential, that means I'm giving it electrical energy, or rather I'm taking the electrical potential energy and converting it into kinetic energy. So my electrical potential energy has been now converted into kinetic energy of that particular particle. Okay. What is the electrical energy given? It will be always the charge multiplied by the potential difference. So what is the charge? It is Q. What is the potential difference? It is delta V. What is the kinetic energy? Well, I can just write it as K, or I can also put it as P square by 2m, or I can just put it as half mv square, depending on how I need it. I think I need momentum, not speed exactly, nor kinetic energy. I need momentum because I need to calculate matter wave's wavelength, for which I again need momentum. So I can just say Q delta V is equal to P square by 2m. Naturally, P will become root of 2mq delta V. It will go under the root because it was squaring that P, so taking roots on both sides. Now we just know what to do next. The de Broglie wavelength is h by P. So de Broglie wavelength will be h by P, P being root of 2 times m times q times delta V. That is the answer. That is the answer, right? So this is how we can find out the de Broglie wavelength of an accelerated charged particle. There are many questions on this. Thank you, Shiv Shankar. Sir, is it valid for moving particle or microscopic? It is valid for, it is valid for everything, but you can detect it for small particles. It becomes significant. So for microscopic, it becomes very evident. For day-to-day objects, it is not, I mean, it's valid, but it is not seen. It's valid for everything otherwise. Okay. I think you should go with the new NCERT. Okay. Just go with the new NCERT because the syllabus has been reduced. So you can stick to the new NCERT. It's a good thing. You must be happy about it. For which of the following particles will it be most difficult to experimentally verify the de Broglie relation? Is it an electron? Is it a proton, an alpha, or a dust particle? Which of the following is it most difficult to find the de Broglie wavelength? Come on, everybody should be able to get this, guys. Everybody. Come on, come on, come on. Think about it. Because wavelength is h by p. If p is very large, wavelength becomes very small, it becomes more difficult. So out of this, the dust particle has the highest momentum. Has the highest momentum. That's the reason why it will be difficult. It will become very difficult for you to detect the de Broglie wavelength. Very good, Samira Sastav. Awesome, Wazim. Let's go to the next one. The de Broglie wavelength of some particle of mass m moving with some kinetic energy E is. Come on, I just gave you the formula. The de Broglie wavelength formula. Come on, guys. I just gave it to you. If you remember it, you remember it. Or else you'll sit and derive. It will take you hardly 10 to 15 seconds. Still, you can get the answer. Is it A, B, C, or D? Is it A, B, C, or D? Yep. Think about it. Thank you. Thank you so much for loving my physics classes, Vishal. Yep. Is it B? Pakka? 100%? Very good. Because I just told you lambda is h by p. And since p square is, or p square by 2m is equal to k, or basically your energy. So p square will be 2me, or rather p is root of 2me. So therefore, it will become h by root of 2 times of me. So that's how the formula even comes. That's all. Kinetic energy is momentum square by 2m. That was the standard formula from which it comes. Another interesting question. What is the relation between wavelength of a photon and the electron of same energy? Very crazy question, because on one side you have a photon, which is light, and on the other side you have electron, which is matter. So on one side we are talking about wavelength of light, and on the other hand we are talking about the de Broglie wavelength of electron. Mind blown. Two different things. Let's try to solve it. First, let's solve for the photon. So for the photon wavelength we have to find, right? So I can say energy is basically hc by lambda. So this is for photon. So lambda p, I can say it is hc by e. hc by e, right? So that's all. I shift this up, e goes down. Now let's do it for the electron. Let's do it for the electron. Now for the electron, lambda is equal to h by p. P we just know is root 2 me. Okay. How about dividing both of them? I think few things might just get cancelled out here and there. So let's just divide both of them. So lambda p by lambda e will be hc by e. H comes down, root of 2me goes up, h goes out, root e by e, right? Just check this out, root 2m, and this is root e, and this is basically your e. Root e cancels, root e cancels, and I'm just left with c root 2m by root e. So I can just write this finally as wavelength of photon by wavelength of electron is c root 2m by e. So I think we just got it. How wavelength of photon and wavelength of electron are related to each other. Speed of light into root of 2 times the mass of the electron divided by the energy of them. It was clearly mentioned that they have the same energy. This was a very, very important thing. We assumed that the energy being same, E. Here also E, here also E. Notice the same energy, right? So that is why I have put the same value, or else it could have been different. Yep. I hope these problems are giving you a good insight of how these topics have to be handled with care. and the delicate difference between particles of light and particles of matter. Very, very subtle difference which you should be aware of. So I have kept some homework question for all of you. This is the first homework question. Make sure you solve it. Please take a screenshot of it right away, right now. Answers I'm not going to show. You will get it in the PDF form in the Telegram group. If you're a part of it, good. If you're not, make sure you are a part of it ASAP. This is the second question. K is the Boltzmann constant. If you are not aware of it, it's okay. Maybe you'll study that in your thermodynamics, right? So it's basically from kinetic theory of gases, KTG chapter. So Boltzmann constant comes over there. Each atom or molecule is in a state of random motion, and the average energy formula you might have studied over there. So maybe that will be helpful in this particular scenario. So that is your second question. Just solve that and let me know the answers in the comments. I'll be waiting to see all your comments. And guys, after this, shall we do atomic structure? Shall we do nuclear physics in the weeks, this week and next week? What say? Let's do it. Let's complete modern physics 2 weeks. What say? That is the challenge. Modern physics 2 weeks. Are you ready for the challenge? If so, put it up in the chat box. Modern physics 2 weeks. Modern physics 2 weeks. Let's complete, including semiconductors. Let's do it all in the next week maximum. Right? That's it. After that, we can go to some other unit. Maybe we can pick up something like AC or waves and SHM, or who knows, whatever. Right? So let's do that, guys. Thank you very much for joining in today's session. Awesome session, I believe. So please smash the like button. That will show that you loved and enjoyed the session, and I will see you more often then. Cool. Thank you for subscribing, and do not forget to use the coupon code CAPTAIN. That's your Cool Captain's code for enrolling into any Unacademy course, be it Plus, be it Iconic, or if you want to join my batch, only, then you also have the NEET Energized batch, which is live right now. The remaining part of the course will be available to you as a live class, and the previous classes as recordings. So check out the link which is there in the description box. Okay. So thank you very much. Bye bye. Captain Shreya signing off. Hasta la vista.